stuff. No? Okay, so effective net area. What is that all about? We have this A effective, and then we have A net. What's the differences between the two? U. Yes, all of you. No, yeah. A effective is equal to U times area net, right? And what is U? What does it do?
Counts for lag.
Hit your buttons. Share your knowledge of cyberspace. Nobody wants to.
It counts for the area that's not transformed into like the other members of the bolts.
Yeah, it counts for the area that has lower amounts of stress in it. It counts for a non-uniform stress distribution, right? Counts for a non-uniform stress distribution. We use this 1 minus x bar over L. And I don't know why it's so bright. I think I can see it in the back and it looks great. It just looks bad up here. So maybe it's still doable. We'll see. I turn the lights off, right? Yeah, who knows what happened. I'm just not going to mess with that. So, how do we calculate U? First of all, what are the values for U? How do we know if there is a U? What do we look for? What's the telltale sign?
An outstanding leg.
There's an outstanding leg, right? Yep, there's an outstanding leg. So it looks like an L shape that's hooked to something else down here at the bottom. Okay, something like that. Yeah, like ding, 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 there's a U. Okay? What kind of ranges of values do we expect to get for U's?
Between 0 and 1.
Between 0 and 1. Okay, so that's a good starting point. Okay? We're not going to go up to 1. U is actually capped out by 0.9. Okay? So it can never be higher than 0.9. If you ever calculate a U higher than 0.9, you've got to cap it at 0.9. All right? Now, and 0 is pretty darn low. 0 means there's no area. Okay? So if you've done some U calculations in the past, you're like, what do you mean? I try to forget all those, right? I don't want to think about that, right? Don't. Okay? You need to get a feel for these things. Okay? Really, U values are anywhere between around 0.6 to 0.9. Does that mean there's values lower than 0.6? Sure, there are. Does that mean there's value higher than 0.9? No, there can't be. Right? Not allowed. Okay? And you'll usually find values around the 0.7 to 0.8 range, but 0.6 to 0.9 is not unreasonable. Okay? Okay, it's good to always know kind of what you're calculating, right? What numbers you should shoot for. What's the equation for U, or how do we find U? 1 minus x bar over L. What's L? Length of the connection. What's x bar? Distance from the centroid down to the plane of the connection, right? Just because it's x bar in this equation does not mean it will be x bar in your manual, right? You got to check. You got to think. Great. Talked all about that. Oh, is this the only way to get the U value? No, there's this awesome table, right? It's in your steel manual. You can use it as well. Which one do you use? Higher or lower? Well, actually, you can use whatever one you want. Okay? But the higher one, right, is the one that you're allowed to use. Okay? It's kind of odd. You're not allowed to do that very often, right, in engineering. So savor that, right? Savor that. So there you go. Okay, so we talked about that. And then we introduced briefly block shear last time. Right? Started talking about block shear. And what is block shear? If we could summarize block shear, what is it all about? What is... Oh, it looks horrible in the back, though. Oh, dear. Okay, that might be right in the middle. What is block shear all about? What is it all about?
Failure and tension on one face and shear on the other.
That's right. It's failure and tension on one face, tension on one plane, shear on the other plane. Okay? Do they happen simultaneously? Not really. And you would never really want to know on a real building, right? Because that means you'd have to be standing right next to something huge that was about to fail, right? And even then, it'd probably happen so fast with gravity load that you wouldn't even know what was going to happen, right? Now, we showed the movie, right? We showed that movie, and that movie is loaded with hydraulics, right? And we're doing it real slow so we can kind of see what happens. And we saw in that movie, we start to see some kind of yielding and fracture on one face, right? And then we saw a fracture on the other face, right? Okay? And it's kind of cool because, I tell you, you guys have hopefully seen block shear before in your life, but when I explain it for the very first time to people, they look at me like I'm nuts. And it's more than they usually look at me like I'm a nut, okay? Because I'm used to that, all right? That's my baseline, how they usually think of me, okay? But if you have the movie, then you got an ability. It's like, see, I'm not totally nuts, right? Okay. Yeah, you know that already. Great. So we've got this welding failures that we talked about as well. It's a possibility for block shear. It could actually happen in the plate or in the base metal. Talked about some situation like this where you could actually have block shear on two different faces simultaneously, right? So which one's going to control? Well, the one that shows the lowest load, right? Causes the lowest load for it to happen. Awesome. We talked about this. We talked about this sheet here on how to design for block shear. And I said, hey, there's this U equation that we're going to have in these problems that we've never had previously. Or we've had them, we've talked about them, but you never really used them. You're going to be using them in this class. Okay? And these U's, we said, you know what, they're similar to the U's we've used before. Similar, but not exactly the same. And they're really for this case when you have some kind of simply supported beam with multiple rows of bolts in shear. Okay, if you have one row of bolt, don't worry about it. U is 1. If you have multiple rows of bolts, what's U equal to? 0.5. Doesn't make much sense to me, but that is what they've agreed upon right now. All right? I guarantee you there will be changes coming up. Okay? But it's to take into account this. Oh, what a great possible question on a future exam. Why is U anywhere between 1 and 0.5 when it comes to block shear, but yet when we talk about just pure tension failure, U can be anywhere between 0.9 and some low number close to 0, right? Theoretically, right? You'd have to explain it to me, okay? It's great essay type questions. Questions in this type of in this class for questions on tests will not be largely mathematical. They're going to be much more about why and what's going to happen. Okay? It'll be math, don't worry, but it's going to be much more about why. Okay? So you're going to need to explain this in a very coherent manner. Okay? So if you don't understand it, now's a good time to ask, right? Or ask your questions. Okay? Okay. Now, if U is equal to 1, we can just use these straight equations, these simplifications. You kind of can feel which one's going to happen first. Is the shear going to yield first? Is the shear fracture going to happen first? That's what you're really calculating here. Comparing is would it rather yield or would it rather fracture? Okay. And after you make that decision, that guides you to whether you're case 1 or you're case 2. Okay. Sadly, when you get a UBS equal to 0.5, you can't use this comparison anymore. So what do? You give up, right? Fire an element program, right? 3 weeks later, you'll get an answer, right? What do? Go back to the original equation at the top, the big nasty one, the big one. If once you take the FE exam or the PE exam, this is the only thing they're going to give you in your book. Okay? This is what's in the book. Okay? They expect you to know how to use it. Okay? All right? All right. Any questions on block shear? It's kind of cool with like a stroke of the pen. I can cover like 4 lectures of undergraduate class, right? It's like, oh yeah, this is easy. Okay, so when it comes down to block shear design examples, we're not going to spend a lot of time. Now, just because I blow through these examples in class and I don't cover them, doesn't mean that you shouldn't be reading them, studying them, looking at every single detail to understand why it's there. This is graduate school, and everything you're given is not covered and described. All right? All right, so if you're not doing that, get to it. All right? Homework coming up. Guess what? Just because it's not on the homework, let's say there's some nuance that I didn't cover in the homework, doesn't mean that it won't be on the exam. It's fair game, okay? It's all fair game. So what's going to be on the exam? Anything I want to put on the exam, right? No, I'm going to try to be reasonable, all right? But I am going to expect you to know everything in the notes thoroughly. Now, I've tried to show you some pretty challenging problems, all right? And again, if these are too challenging for you to start out with, you know what? Flip around and look at some other ones, or go back to a steel book, okay, and look up some more basic ones, okay? So, but I wanted to show you some weird stuff, okay? Because we're going to talk about a lot of the weird stuff in this class, all right? And this is actually a connection that's extremely common in trusses, okay? Extremely common on a diagonal of a truss, okay? You have a diagonal that comes into a gusset plate, okay? And the way, because of the geometry of the situation, you don't want to make a funny looking gusset plate just so you can have an equal leg weld on both sides, right? We're going to save some steel, right? We're going to cut this gusset plate back. Very, very common. When it goes to do the welds, where you're going to weld, well, they want to weld around the outside, right? They're going to weld it all down. They're going to want to know how strong it is, how thick does it need to be, you know, whatever. Okay? So how do you handle a problem like this? Well, first thing you should say is what? Outstanding leg. Right? Right. Great. Outstanding leg. That means there should be a U. Right? Yeah? Yeah? Okay. So, first though I do my yielding check. There's no big deal there because where's yielding occur at? In the bulk of the member. Right? In the bulk of the member. Nothing really strange going on out there at the end. Now let's do fracture. Okay. I say assume the outstanding leg is not connected since the weld is only 2 inches in length. What? What I'm trying to say here is that if we look at this connection, we look at this angle, this piece, the bottom piece of the angle, is obviously connected with the 5-inch weld down here, right? And it's connected also with the 2-inch weld up here at the top, right? Now, if we start to think about what the load transfer is going to look like from this angle, if we drew our picture, and keep in mind on one side we have 5 inches of weld, right? And on the back side of this, we have 2 inches of weld. You with me? Okay, so if I kind of drew, this is 5 inches of weld, and on the back side I'm going to draw it here, we have 2 inches of weld. You with me? Okay. And we have stress out here in the member, and way away from the end, what's the stress? Look like it's uniform, right? P over A, the flow, the stress, the whatever is uniform. So now we've got to think about, we all realize there's a U, right? As soon as we saw the problem, we said, ding, 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 there's a U. Okay? Now, the way to typically use the U would just say 1 minus X bar over L. Be a computer, be a robot, be what we're used to doing. Think about what the X bar is, okay? And think about what the L is. And what L would you use? One length is 5 inches, and one length is 2 inches. What L would you use? The longer of the two, one person says. Okay? Why'd you say that? Okay? You could say the longer of the two because that one's going to probably carry most of the load. Yeah, you could say something like that, and that's actually the logic that we're going to get out here, is this idea that this is the length that's actually hooked to the member, right? Right. So we're going to really want to get this stress out of here as much as we can before we get to this 2 inch. It's just not going to help us that much, right? right? Now, 5 inches is one way to handle it, and if we have a constant up here at the top, and I divide by 5, that's going to make that constant smaller, right? Right? So 1 minus a smaller constant equals kind of a less conservative number, right? But that's one way to attack the problem, right? It's one way to attack the problem. Okay, now, could one maybe see where you might use the average of 2 inches and 5 inches? You know, you'd say like, well, I got 5 inches on one side, and that's going to make this number smaller, and it's going to make my number not as large, right? I'd rather be conservative, right? Right? So I may use the average between 5 inches and 2 inches. Okay? Then I can see where people would argue 2 inches is the number that you should use. I think that's much tougher to argue. Okay? I think that's a lot tougher to argue. I think that's going a little bit too far in one direction. All right? But I could see where one person would say, I'm just going to look at the math, and the math, I get a more conservative number if I use a 2 down here instead of a 5. Right? Do I? Is that right? Is that right? You get less, don't you? We made some mistake here. So if, what would be helpful to look at like 1 minus 0.8, we have 0.88 over 5, and then we have 1 minus 0.88 over something like the average between 5 and 2, so that's 7 divided by 2 is 3.5, right? And then we have 1 minus 0.88 over what? 2 inches. Now what I'm doing here is I'm bounding the problem. Okay, I'm saying what are some choices that we could use, right? I'm saying what are our u values going to be if we bound the problem and look at these things in these different ways. So if I use 0.88 divided by 3.5, so I get, oh yeah, I am good here. This is a 0.75, and if I use 0.88 over 2, and I add, I get 0.56. Okay, so this has been getting more conservative, right? So I've got anywhere between a u of 0.82 and a u of 0.56. You with me? So which one do you use? Well, that's where you got to kind of rationalize this. That's where you got to kind of argue. Okay? It's not clear. There is no guidance in the code. It doesn't tell you what to do. You got to think about this. But we did the math, and we say, you know what? Depending on what I assume, it could be a u of anywhere at 0.82, or it could be a u of 0.56. It really depends over what length I'm assuming this load is transferred over. You with me? Okay. So you would want to decide which one you feel comfortable with. Okay. Now, just to ultimately bound the problem, what is one way I could work this problem and not have to even worry about any of these assumptions? Well, I could actually assume my load is only transferred by my bottom plate. You with me? That's pretty conservative, isn't it? Okay, and I can already see the deer in the headlights look that engineers get when they start to have to use engineering judgments. Which one do I pick? Which one is right? Guess what? That's what this class is inadvertently all about. Okay? Big emphasis. So if we did do something like that, then we would use a u value closer to 0.5, right? Yeah? Right? Depending if it's an equal length leg, and it is, it's a 3 by 3 by 3/8, right? So using that conservative assumption, using just the bottom, I would end up coming up with a u equal to 0.5. You with me? You with me? Now, what you have to do is you have to look amongst these, and you have to decide on which one you're comfortable with. Okay? Now, I'm not sure this is the best way to handle this problem. But if you notice, if you follow the math all the way through, when it comes to the area that was used, let's see here, 0.75 times 0.82 times 4.22, 150 kips. Okay, so this is a pretty loosey-goosey type answer. We're taking the entire area. We're taking 0.82. I think this is a little unconservative. A little unconservative. I mean, this is actually working it the way, assuming the welds were the same length on both sides. You with me? And they're not. Sure, you wouldn't expect the load transfer to be the same on both sides, right? Right? You wouldn't. I wouldn't expect it to be. I wouldn't expect to assume that there's 5 more inches of weld over here where that load can leave my cross section when it's not actually there. You with me? Okay, so these are the type of things that you have to see and catch and say, you know what, this is a little bit unconservative. Okay, so what number should I use? Should I use possibly 0.75? Should I use 0.56? Or should I use 0.5? Come on, somebody pick one and explain to me why you would use it.
Well, if I made the assumption that I didn't want the weld to break, period, I would use the 2-inch weld because that's the one that's taking the slope. I don't want the weld there to crack because as people receive it.
Okay, so hit your button first of all, and when you're talking, and second of all, when we do a calculation like this, I'm with you. The statement is that if I'm very concerned about the integrity of the weld, then I'm going to assume that my plane of failure is somewhere back here, right? Is that what you're saying, Miles?
Yes.
If you're very concerned, and you are concerned about welds, for sure, right? The one thing I could say to that is that this is not a weld check per se. This is a cross-sectional area failure check. And when it comes to the weld checks, if you want to not include this weld over here because you're worried about, it's kind of eccentric loading there going on, right? That's up to you, and that's a very good idea. So do some things like that. One thing I could say to counter that is that the design and welds already are extremely conservative. Okay? And you're probably going to be okay in this type of situation. Now, if these things start to get way different in length, then what you're talking about becomes a lot better idea. A lot better idea. You with me? Okay? But we're talking about cross-sectional area failure. Which one's right? And the answer to that is, who cares which one's right? We don't have time to figure out which one's right. What do we want to do? We want to what?
Get money.
We want to
Pick
get
one and
money.
go.
We want to get designs done. We want to go home and see our families and watch TV, right? We want to do other things and sit around and agonize about this decision, right? We don't want to hop on a computer and spend 2 weeks on it analyzing. Now, sometimes you do, okay? If it's a critical connection, if it's really that important, if it's going to be done over and over again, that's your job, okay? Go do it. On a connection like this, okay, oftentimes you don't want to spend that much effort, okay? You don't want to. So you got to come up with something that's conservative, right? That's still going to work, okay? So if you want to be ultra conservative, you can usually go with something like the U equals 0.5, and no one's going to argue with you, except for to maybe say that you're too conservative. That's where you'd like to be, right? Okay? So the 2 inches, I'd say that's solid, okay? That's a solid assumption. 3.5, I could see where that would be argued. I could see where this would be unconservative and not be a good idea. Does that make sense? Okay? So this is another example of a test type question we could ask. I could say, I could show you this, and I could say, come up with the capacity for the fracture. Explain all possible failures. Pick one. Give a rationale on why that one's the best. For you. Alright? These are the type of questions we're going to be asking in this class. These are the type of problems that we're going to be learning how to solve in this class. And when I come back to it, I said this before and I'll say this again, there is no one right answer, except for that answer is wrong. That answer is wrong. This answer could be right. This answer could be right. This answer could be right. Now it comes down to which one do I believe in the most and why? Or do I want to be conservative because I'm worried about this? You with me? Any questions on that? Because you better get ready. Because it's going to happen over and over and over again.
I'm still trying to come up with why you got the U at 0.5.
Okay? A U of 0.5 would be if I assume my top leg isn't even there.
Oh, okay.
I assume it's gone. I assume I'm only counting on the bottom member to carry load. The bottom of the element to carry the load. And since the lengths are the same, it's a 3 inch by 3 inch by 3/8. That would be the same thing as assuming just half the area is helpful, right? That would be a U equal to 0.5. Okay, you're probably not used to making these decisions. You're probably not used to doing things like this. Don't worry, okay? But if you avoid it because you're scared of it, you will never get better at it. So it's time to jump in. So let's talk about block shear. About block shear on this same problem. We have 5 inches, 3 inches, 2 inches. Okay, we're going to use the angle, the boundary of the angle. Okay, people always like to say, yeah. If this is going to be failing in the member underneath, then it's going to be a little bit longer, right? It's going to be a little bit longer, right? Because you're going to have that toe of the weld. I don't want to think about that. I don't want to think about that. Okay. Instead, I want to make a conservative assumption and say I'm going to ignore that this is going to actually happen on the outside and it's going to be a little bit longer. And instead, I'm going to use the actual perimeter of the angle. Very, very common assumption. Extremely common assumption. Okay. So we do the same thing here. Where our UBS is equal to 1 in this case, because it's not a simply supported beam and shear with multiple rows of bolts, right? So I get to use my 0.6 FU A and V, 0.6 FY AGV, and I find 91.5 kips controls. Now, guess what? We spent all this time agonizing. All this time agonizing up here on which U to choose. Which U to choose. When it comes down to, and you start to do the math yourself on all of these, you're going to find in the majority of these cases, I think almost all these cases, that this is still going to control. Still going to control. So then you go back and look at it and say, why not go ahead and choose the most conservative one? Right? Because this is still going to control. You with me? Okay, I see thoughtful eyes. Is there any questions? The first mind-melting question example. Many more to come. Don't worry. Okay. So, problem like this. Got an angle. Got bowls, diagonals. What are we going to check? Yielding, ching, fracture. Notice I checked 2 paths. Straight across and then at an angle. Hey, we know how to do that, right? S squared over 4G, right? Right? Yeah. Great. Block shear. Oh, Nelly. Diagonals and block shear? Sure, if you can dream it, then it can happen. Okay? So I draw 2 failure cases. You are going to be expected to draw the failure case for every single calculation you do in this class, especially when it comes to connections. Okay. So I draw failure case A, and I call it case A. I've labeled it clearly. I write out case A. I calculate my ANT, my ANV, my AGV, and how do you handle a diagonal here? How do you handle a diagonal? Well, believe it or not, if you look in the code, there is no guidance. There is no guidance for block shear calculations for ANT on a diagonal. No guidance at all. However, right up here, when we did our fracture calculations, when we go to from A, B, D, E, we use an S squared over 4G, and that is in the code, right? And that was finding a net area of tension, right? Yeah? Helped with that. Okay? So, why don't we do the same thing? Why don't we use the same procedure? Why don't we use an S squared over 4G type term when we calculate A and T? And that's what we did right here. I got a question for you. I got this 2.5, okay, 2.5 inches plus 1 1/4. I'm adding this dimension, 2.5 plus 1 1/4. Then I'm adding in this diagonal, right? Because it's at a diagonal, right? S squared over 4G. Now I'm subtracting out 1.5 7/8. Where are these numbers coming from? Where's 7/8 coming from? Diameter of the hole plus slop, right? How come I'm subtracting out 1.5? What's that?
It only runs through half the bolt.
Right. We got one bolt going through here. Got a half a bolt going through here. Draw the picture. It will help you not make these mistakes, right? It's going through 1.5 bolts. Great. Get A and T, get A and V, get AGV. Calculate case 1. Oh, it controls. Calculate. I get 74 kips. Now I check case B. Over another diagonal and down. Now, it's hard to tell when you're just getting started out what's going to control. It's hard to tell actually if there's another case you could check here. Hole, 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 hole. Fracture, 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 and then go straight across. Right? Is that possible? It is. Should it be checked? Sure. Sure. Sure it should be checked. Run the numbers. See what it says. Okay? What you're checking, what you're comparing here, is there more area involved to go straight across, or is there less area, however you want to look at it, or is there less area involved to go straight across through no bolts or half a bolt, or to go at a diagonal and go through 1.5 bolts? So the math is doing it, right? It's comparing that for you. Putting them on a scale and deciding which one's going to happen. Okay? Yeah. Check it. Should check it. Okay? Then we do B. Wow, well this one's a little bit odd. This is a little bit different because we don't usually think about leaving one hole behind, right? But it's possible, right? And heck, you could start talking about leaving 2 holes and 3 holes and 4 holes behind, right? Yeah? Okay, so let's stay with me, bear with me on this type problem B here. Let's work. We find our A and T. I say it's the same as what I had before. I have my A and V, my AGV. I start plugging in all these numbers. Now, when I solved for my capacity in the past, I wrote down just my phi PBS, or what my equation was. I basically used this equation, or this equation, right? Straight, right? I'm solving for the load that was needed. And we're going to notice on this problem where we leave out a bolt, we don't just solve straight for the load. We're going to notice when we leave a bolt out that I'm actually going to solve for 4/5 of that load. Why?
Because 1/5 of the load is not taken into account because of the bolt.
That's right.
Not being in the
We
groove.
left the bolt behind, right? Right? And we're assuming that 1, 2, 3, 4, 5, 6, no, 5. We're assuming there's 5 bolts, and each bolt taking P over 5, right? And we're only holding up, that fracture plane only involves 4 bolts. So it only holds 4/5 of the load. You with me? So on the left-hand side of my equation, instead of just solving for P, or phi P, and I solve for 4/5 of that. Okay? And I find out that actually this controls by 0.3 of a kip. Not that big of a deal. Not that big of a deal. Now, why I'm showing you this is not to scare you and not to make you think that you have to calculate all these things. But what I'm trying to show you with this is saying, if you do have to calculate these things, you can, but let's think about how I got to these answers. Because if I asked you to do something like this on the homework, you'd go in and look in your code and you'd say, maybe you look at your code, you'd probably just say, I've never seen a block shear on a diagonal. Oh, I'm not going to check it. I'm just going to do this one because I don't know what to do. That's never a good answer. And that's not a good answer in this case either. Okay? You have to use your rationale. You have to say, like, okay, when I'm calculating block shear, I know that I need AGVs and ANVs, and those are no problem. I can get those as I always have. It's the ANTs that are giving me the issue, right? The net areas in tension that I don't really know how to do. What is a conservative or good or rational way to handle that? Have I worked any problems similar to that? And hopefully there's a bell that goes off in your head that says, yes, you have. And that's when we were just doing the pure s squared over 4g calculation, right? So I'm going to use what I know from that to help me out with this problem. There's going to be examples like this that happen in this class over and over and over again that aren't apparent. But guess what? Through using logic, you can come up with a good way to attack the problem. Okay? Okay. Any questions? Better look at these in detail. This is a more straightforward problem. You know, the only thing that's kind of odd about it is that there's two failures that happen simultaneously. Not that big of a deal. So it kind of depends on how you want to solve for your areas. And actually, this is actually happening at 4 different places simultaneously. 2 in the top and 2 in the bottom, right? The other thing that's kind of unique on this problem is that when it comes to doing a fracture calculation on this cross-section, okay, trying to find a U for that cross-section, you'd say, is there an outstanding leg? Not necessarily, but I'll ask the question a different way. At the connection, would you expect all pieces or plates to be loaded equally? The answer is no. And the reason why is because there is no load transfer at this point. There's no way for that load to escape. So when the load is barreling down here, it's going to go in this direction, and it's going this direction. You with me? So when I go ahead and I do my U calculation, I wouldn't expect to have a uniform stress distribution. So I'm going to expect to need some kind of U. How do I work this problem?
Divide the I-beam in half and treat it like an angle.
Exactly right. You divide the I-beam in half. You actually work it as if it's 2 T's that are stacked together, right? Because if this was a problem with a T, the plate on the back side with bolts, you'd know how to work that problem, wouldn't you? You'd know that this is, outstanding leg, ding, 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 right? Yes, this is my X bar, right? This is my L. I know how to do that. You have to think sometimes, all right? Sometimes you get lucky and you've seen a previous problem that's similar to it, and that can be helpful. But what you need to be doing is training yourself to look at problems and thinking about movement of forces. And thinking about what are some of these things that I take for granted or that I assume to be true that I don't like to think about that may not be true in this situation. You with me? Any questions? Awesome. of the previous failure modes we talked about involve the failure of the member. Now we're going to focus on the bolt-related failures. We'll talk about welds coming up in a little bit. But bolts, when bolts fail in shear, the following occurs. Hopefully you've all talked about bolt failure. If I'm pulling it across with two plates, I've got, in a sense, this load on one side, this load on the other side, and the bolt itself is in shear, right? Great. There's a great, awesome table 7.1 in your steel manual of choice. It gives you all kinds of cool numbers about shear capacity of bolts. In that same table, and I think it's 7.2, I think it actually talks about tensile capacity of bolts, which also can be very useful. And we will be using them in this class as well. Table reports things with threads included and threads excluded. And if you haven't seen this before, this is just, is the failure assumed to be in the threads, or is it in the shank? Right? It's very common to have a blank part or a flat part and then a threaded part. Why don't they thread them all the way up? More money, right? Costs more money. They don't need to thread them all the way up. Why would they? Right? Great. So it's very common for engineers to assume an N, that your threads are included in the failure plane. Extremely common. I've actually never worked in a design office when it wasn't assumed that way. Okay? And why do we do that? Because it's easy. Because it's simple. Because we don't have to do any geometry calculations to see, for that size bolt, what is the shank length? And then what is the geometry of my actual connection? How far do these plates actually come down? And where do they bear? Also, guess what? I'll have parts that may have threads included, and then I may have parts of my connection that'll have threads excluded. Guess what? Make the easy assumption. Assume they're all included. You with me? Okay. So not every bolt is also in single shear. It could be in double shear, could be in triple shear, quadruple. Actually, I think triple shear is impossible. Spent a lot of time working on that. I think quadruple shear, there's all kinds of different shears. Okay, I've seen, it's pretty common if you're ever in, maybe you would be. If you're ever in Pittsburgh, okay, or if you ever see these, there's these common types of trusses they used to build, and I can't remember their names right now, but they have these huge pins. And off these huge pins, they have an I-bar going one direction, an I-bar going the other direction, an I-bar in this direction, in this direction, in this direction, in this direction, over and over and over and over and over and over and over again. Why do they do something like that? It's so that they can take a pin, and instead of making the connection in one place and only having one shear plane, they can force multiple shear planes to happen. Right? So in a sense, by making these members smaller, they can also make their pins smaller, because they're spreading the area out where the shear failure happens over. Dividing and conquering. Well, that definitely looks like a good future homework problem for you guys to do. You can just see the scared look in the eyes. So that's what they do. That's what double shear, triple shear, quadruple shear is. This is very common. And if you're ever in Pittsburgh, there's a famous, I think it's called a lenticular truss, and it uses these type of connections. Okay, and that's why they did it. It's just to make their pins smaller. Okay, save money on pins. Last topic we'll talk about. We can also have these things called localized failures around the holes, or we're going to referring to them as bearing and tearing. Right? Bearing and tearing. What bearing and tearing are is where you have a bolt that may be too close to the end, and it would rather tear out. The failure plane would rather be here and here as opposed to straight across. Right? That's a tearing check. And we'd have this calculation if one wanted to do what the tearing check was. And then there's this thing called a bearing check. This idea that, you know what, I'm going to move these holes way away from the ends, but for whatever reason, my plate becomes small, really, really, really thin. What will happen is you'll get localized crushing and buckling. And I'll show you a movie. I don't think I have time to show it today, but I'll show you a movie on Friday of both of these happening. Okay? But what it looks like in bearing happens, looks something just like this. You see a localized buckling or crushing. If we were to take a cross-section and look at this from the side, this is what it looked like before the load. This is what it looks like after the load. Okay? The bad thing about this is you started out with round holes, and you ended up with slotted holes. That means your connection can lose geometry, can change geometry because of localized crushing at the end. Okay? And that's bad. You don't want that. You don't want the wind to blow and your structure to move and not go back. Right? Right? The leaning building. Everyone will make fun of you. Okay? Okay. That's bearing. We don't like that to happen either. Believe it or not, only one of these will control at each bolt interface. At each bolt interface. And the thing that decides everything is L sub C versus the diameter of the bolt. That's what it's all about. L sub C, this clear distance from the edge of the bolt to the end of the plate. L sub C versus the bolt diameter. If L sub C is greater than 2 times the bolt diameter, then bearing is going to control. This is the bearing calculation. If it's less than or equal to 2 times the bolt diameter, tearing is going to control. Now, remember, this is important. Remember, this has to be done for each row of bolts times the number of bolt rows in the connection. What do I mean? If I have this connection, something like this, I have to think about, and I'm just going to talk about the top plate at first. Okay? You could actually do all of these calculations again for the bottom plate. Might have to. Depends on what the thickness is, and it depends on what the spacings are. But I can tell you right now, this L sub C is going to be something like half a bolt diameter, 3 inches minus half a bolt diameter, right? And this L sub C is going to be 1 1/4 minus half a bolt diameter, right? So this L sub C is going to be smaller, right? And the thicknesses are the same, right? So I can tell you right now, I know that the top plate is going to control my bearing and tearing calculations. Okay? I know. If you don't know, work them all. Prove it to yourself. Okay? Figure it out. Think about it. But I can tell you I know it's going to happen. So I'm just going to be checking the top. Now, I've drawn a picture of what bolts I'm checking. This is really important. I know this is done at the end of the class, but this is crazy important. Please, something, 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 something. And it's over. So it's great for cyberspace, right? Because they'll think they missed something really important, right? And we'll talk about it next time. This is really